Yeah, thank you very much for the introduction. As you said, I'm from ETH, specifically from the systems group at ETH. And what I'm going to present is our work over the last 3-ish years in making board management controllers more reliable, safer, and more secure. This is work by a lot of people. Some of them are on the slides. The one in the top row, so that's me, Ben, and David, are actually also here at the summit. So if you later want to talk to any of us, please stop by. Notably, there are a lot of people that are not on the slides. Again, notably a bunch of brilliant undergrad students that contribute to this project. But first, what do I mean when I say board management software? So what you're seeing here on the slide is a modern 2-socket server board. It has 2 CPU sockets. Now, it turns out that a board like this is so complex that you need a computer in a computer to manage that thing. These computers are called BMCs, or board management controllers for long. And they manage everything in the system. They manage the firmware that is running here on the CPUs, and that goes down to managing actual power on the system, turning individual regulators on, delivering clocks to system components, everything. The system doesn't turn on without the BMC doing its job. Pushing the power button will just not do anything. And all of that happens without the operating system running on the CPUs here even really knowing that that thing exists under the surface. And so that makes this BMC the root of trust in such a system. And now you might be asking, why does a bunch of academics, we're a university research group, why do we know all this stuff? Well, it happens that we built this computer. It's called Enzian, and it's a heterogeneous server class system for conducting better systems research. There are a couple of things that are special about Enzian. The most notable thing is that actually one of these CPUs is not a CPU, it's an FPGA. It is still cache coherent though with the CPU on the other socket. However, if you look at the system from a board management view, as seen from the BMC, it is absolutely representable of a 2-socket server system that you can buy off the shelf today. And as I said, without the BMC, nothing on this board works. So naturally, if we wanted our system to work, we had to write firmware for this thing. And the question is, how do you do this? And we had to learn the hard way that nobody really tells you. Traditionally, the software that is running on those systems is closed source. So that means we cannot look at it. We cannot get good tips from how that software works, as you usually do in operating systems, right? But even more crucially, it means that you cannot expect this stuff. You can inspect it. You cannot look at the source. You don't know what's running on there. This runs at the heart of your server, and you have no clue what it is. And actually, if you type BMC into vulnerability databases, maybe we don't want to know what it is. So recently, this situation has somewhat improved. Open source implementations for board management controllers have popped up. One of the most prevalent one being OpenBMC. It's also what we're currently using on Enzian. However, OpenBMC runs on a Linux kernel. It uses C++ components. It uses Python code. It uses bash scripts to glue it all together. So just baseline, anything that is a vulnerability in the Linux kernel is now a vulnerability at the absolute bottom of your server. And the operating system that you usually care about, no clue. Let me just illustrate it. To make things worse, these things are usually connected to the network because, of course, you want to remote manage your server. Now, somebody takes over the web server, abuses some sort of vulnerability in the kernel, compromises your power manager. Attacker now has control over your system, can turn off the lights at any point, or turn on the heat in your data center to quite uncomfortable levels. So clearly, this is not what we want at the heart of our compute infrastructure. Before we look at how we are trying to fix this, let's look what we're sort of up against. So the core task of the BMC is to keep hardware safe and operational. Hardware can break in many ways. 2 examples, power management failures. If you don't turn it on correctly, it doesn't turn on or even breaks. Firmware, the other example I'm going to bring up is firmware. If the firmware isn't right, system won't boot. Your operating system doesn't even load. It won't boot anyway. So we have a bunch of critical components in this system that we need to trust if we want to trust the BMC. However, we also have other components in the system, like the web server I mentioned. I have another example of a remote console here. We cannot put the same trust in these systems because A, they're not going to be, not all of them are going to be as rigorously engineered as our trusted components, and B, they face the outside world anyway. So there's no way we want to put the same trust in a web server as we put in our Power Manager. So we have different trust levels in the components, and we have two major ways of how these components could be compromised. One is erroneous API calls. So use the regular API to the components, but do something funky with it. So somebody uploads faulty firmware to the web server, gets flashed on the system doesn't turn on anymore. And the other one is through vulnerabilities, as I showed before, maybe through a kernel exploit, compromise the system. Note also, even if we assume that we are in a non-hostile environment, we don't have attackers, we still worry about this because this could just happen because there's a bug in the system somewhere. So what we really want between these components is isolation. And we have seen versions of this slide many times already over the past 1.5 days. So we all know what's going to happen. What we want is SCL4 under here that guarantees isolation. Thank you. So this is the architecture for our trustworthy BMC system. We have SCL4 that guarantees isolation between the components, and we have trustworthy components. However, of course, the isolation is not everything. If we want to trust the entire system, we also need to have a way to engineer these components trustworthy. If there's nothing correct in there, there's nothing that the SCL4 is able to save, right? So we have 9 Enzian machines at the moment. They work. People are doing research on them. They currently run OpenBMC. And so we have to upgrade the system in place. And so we're applying the cyber retrofit strategy. What we have right now is SCL4 running on the BMC, the previous OpenBMC system virtualized on top of it. That's our starting point. Of course, this doesn't give us any additional security, but now we can start picking off trusted components. The first one that we've been looking into is the Power Manager, because arguably it's the most critical thing that the BMC does. Without the Power Manager, nothing works. And if the Power Manager makes a mistake, nothing will ever work again. So in the following, I will show you 2 pieces of work as an example for what we did to get a trustworthy Power Manager. Now, why is it even hard to turn on a computer? I said that. The reason is power in a modern system is distributed through a network that looks something like this. On Enzian, we have 30 plus regulators and about as many voltage, current, temperature sensors. And again, not a speciality of Enzian. Any modern server the power network will look something like this. If we zoom in on parts of the circuitry that supply the FPGA, we can see where the challenges are. First of all, modern chips often, or actually always, need multiple voltage inputs. They will have different voltages, and we need to configure every rail in the system with the right voltage so that everything that hangs off of it works correctly. So that's the first thing. The less obvious thing is order. Again, here there's a bit more obvious when we look at this MAX 15301 supplying the MAX 20751 here. Obviously, that thing has to turn on before that thing can turn on. That's an obvious ordering constraint, but also the FPGA will have ordering constraints on its inputs, and that is because in silicon, if you make a sequencing error, that can trigger effects like, for example, latch up, which is essentially equivalent to a short circuit. So suddenly you turn on the power in the wrong way, your FPGA dissipates a lot more power that it can handle. And yes, smoke, no fun. So we need a better way of doing this. And what we're proposing is we model and I already hinted at it with how I showed it. We model this network as a directed graph. And then we have components on the edges. Constraints on the edges that tell us what the voltage would be. And we also have constraints on between edges that tell us in what order what needs to happen before what. That gives us a constraint satisfaction problem. We throw it as an SMT solver, and the SMT solver comes back with two things. A solution for the state that we want the system to be in. So if we want to say our system has to be on, the SMT solver will tell us, well, then this rail needs to be this voltage, and so on. And the second thing it's going to come back with is a sequence of steps that we do for transitioning the system from the current state into that desired state. So for example, system is off, we want it on, here's what you do. Now, we do this offline, we pre-compute these sequences, and we can do that efficiently enough for offline use cases. By the way, we published this in a ACM Transactions on Embedded Computing Systems paper last year, and that these are the claims that we demonstrate in the paper. We also demonstrate that we can use it on real hardware. So our sequences do work on Enzian. They turn the system into an operational state and back into an off state. And the benefits we get is we have more confidence in our sequences, because this graph, while not being large in terms of a graph, it's still large enough that if you try to do everything manually, then with all the subtle interactions between different branches of the graph, it's just very error prone. With automation, where the SMT solver deals with that, where we can look locally at each component, a lot of the sources of those errors are eliminated. And crucially for this talk, a model like that lets us actually talk about what correct behavior is for a system, for a power manager. Namely, it is satisfying all the constraints that arise from our model. So if we look back at our architecture diagram, we now have a trustworthy power sequencer. Now, this thing knows what to do, but it doesn't know yet how to talk to the hardware. It needs to talk to all these regulators and actually make that sequence happening, or make that sequence happen. And so one other thing that now came out of this Enzian project is we started looking at how do we model these types of hardware interaction. And what we looked at is how do we model I2C. I2C is a widespread low configuration bus that is used exactly for this sort of thing, configuring regulators on a board, this type of configuration. On Enzian, actually all the regulators are controlled over I2C. There's a standard for this. As it is with any standard, there are devices that implement that standard partially. There are devices that freely interpret the standard. And there are devices that just outright violate that standard. And on top of that, of course, the standard is not always very clear on what it actually says or wants to say. So this is what an I2C, a simplified version of an I2C bus looks like. It's a controller responder-based protocol. So we have a controller that sends requests out on the bus, and we have devices that respond to those. So in my exam, we have a bunch of devices, and what we're going to look at is this voltage regulator. So what we want to make sure is that when we send a request to the controller to tell the regulator to set a certain voltage, that the controller translates this correctly to electrical signals on the bus. They're transferred over, and the voltage regulator interprets this as a voltage set action. So we want that when we request the voltage change is going to be implemented by the regulator. Again, this is work that we published last year in the SPIN conference. And how we approach this is we have a layered specification, because, as I said, each of these devices could interpret the standard a little bit differently. And so each device has its own protocol stack, its own specification stack. We can reuse layers, but if on any layer the device is not compliant with our standard implementation, we can swap it out and do whatever and write down whatever the device actually does. Now, to figure out whether all these interactions are correct, we use spin and model check the entire thing. So we model check that all the interactions interact in the way that we want them to interact with each other, right? That's not all we can do. We can also generate C code from these specifications, and that C code runs on real hardware and controls currently on a Raspberry Pi an EEPROM, but we are working on porting this to the NCN BMC. So, I2C driver, trustworthy, nice. There is still a little bit of a gap. We write these specifications by hand, so who tells us that the hardware actually does what we think it's doing? Now, we're trying to solve this problem, and we have early work for this, by not just synthesizing C code from those specifications, but actual hardware, actual IP that we can put on an FPGA, which, for other reasons, the NCN BMC happens to have. So we can even close that gap and make strong statements about how the driver is talking to the device, that interaction is correct. Now, as I said before, the BMC is not an isolated system. It exists within a bigger system. It's a computer in a computer. So for example, somewhere out there will be a CPU. As I said before, that CPU needs firmware. And for a modern CPU like this, it's not uncommon to boot 3 stages of firmware before it even loads the operating system. And so there will be some flash memory or something, and the firmware manager needs to provision the right firmware for that thing. Now, that also means the firmware manager needs to maybe talk to the power manager, because it maybe needs to turn on that flash before it can actually program it. Furthermore, maybe you want still, even if you want to be able to upgrade your firmware through the web server. So this web server needs to talk to the firmware manager. We have multiple CPUs or FPGAs in our case, in our system. Is it possible, so that's the other direction of this arrow, is it possible that one CPU requests a firmware change in another CPU? Or maybe the power manager needs to tell the firmware manager to, while the system is booting, load some volatile firmware. For example, program a bitstream onto an FPGA before that thing even talks to the rest of the system. And then last but not least, when the OS on the CPU, for example, shuts down, it needs to be able to tell the power manager, hey, I'm done, you can turn me off. So, and my other examples from before, they have their own communication patterns. So in summary, we have a lot of components on the system of different trust level that talk to each other, from software to software, but also from software to hardware. And even so, that flash memory will not have the same trust in the system because it's shared with a CPU that runs user code, right? So that's a lot where our current work is going into specify those interfaces, model the hardware, have accurate hardware models to figure out what we need to be able to do so the system is operational, and what is the maximum we can do before we trash any sort of guarantees that our nice system now hopefully gives us. We're also, so the pieces of work I showed, they are currently isolated, but we are working on integrating them into an SCL4 component that we can actually run. So that's one of the next steps, that we actually run this stack on the live NCNs in our cluster. So we don't just have CPUs out there around this BMC, we have tons of other hardware. Hardware is getting more and more diverse. And the days where just your CPU used to think and run software, they're over, if that statement was ever true. We have FPGAs, GPUs, all that sort of thing. Everything talks to the BMC. The BMC has to manage everything. Everything talks to each other. All of this is interconnected. So really, if we want to look at what the operating system, what the system is that runs on such a platform, we have to look at all the hardware and all the software in the system as a whole. And so if we want to build truly holistic, trustworthy systems, then making the BMC trustworthy is an important first step, but eventually we'll have to look at all of this as a holistic system if we really want to be platforms like this trustworthy. And with that image, I'm done, and I'm happy to take questions.
Thank you very much. A slightly scary picture, and the first question.
I like your world domination agenda. And I'm looking forward to SEO4 shipping on the BMC of the millions NCN. In the meantime, Is there a chance of it shipping in a similar thing, reusing your work on other machines?
So yes and no. In principle, yes. So we're building this system, but once we have figured out how to integrate all of that and make it work on SEL4, then in principle, yes. The problem that we have is, for this to work, you need a lot of very low-level documentation on the system. We have it because we built this board. We have schematics. We have data sheets for every single component. We can switch out any piece of software on the system, basically, that we want. Usually, manufacturers of systems are not quite as generous with giving you access to that sort of documentation. I'm pretty sure that if we had the same level of documentation that actually lets us properly specify what the BMC needs to do, we could pull it off, yes. In principle, yes.
2 more questions.
Did you have to make any changes to the SEL4 in order to support your platform?
We're not quite that far along yet. So we have, I had a student recently who brought up the virtual machine on SEL4 as a CamKeys component. Ben has been working on building a I2C driver. I don't know if you want to maybe talk about that more. I'm sure you'd be able to answer that question better. Yes. So, and that was also based on CamKeys. We met some pain points in there. We have not gone to the point where we started modifying code in SEL4. We sort of worked around the issues that we saw to get our proof of concept running. But we're really excited, for example, about the SEL4 core platform, which should make building systems easier. The driver framework is one thing that is going to be really helpful in building a system like this.
Cool. One more question here in the back.
Yeah, so I'm just wondering about the overall target audience, let's say. Maybe this makes it big and you have it in production. So let's say there's iDRAC Enterprise, right? Which has their own entire operating system, basically. So how does this integrate well with that? And the other question slightly is, if the web server is basically never to be trusted, how do you make sure that the web server doesn't screw around with the power manager? Because it still has to communicate with it. So
yes. So for your first question, we're a research group. We do not build products. We are investigating how you would build such a system so it could be deployed on servers. We're not so sure that we want to there are a lot of standards out there. There's IPMI, for example, for managing it, which apparently has huge security flaws in it. They now have, I think the newest one is called Redfish, which is run over HTTP, which you really don't want to do if your CPU talks to your BMC. It's hard for me to say how well it would integrate. It's not a priority for us because we as academic researchers, we have the freedom of just rematching in that entire system and building it the way that we think it should be done. If there's a migration path, I don't think we're sort of at a point where we can answer that already because we don't quite yet know how the system is going to look like. But if we get people interested in this, if we get industry, if iDRAC comes to us and talks to us, that would be very interesting to see what they think about this. Yes. And your second question was about the communication between. Maybe I go back one slide; it's a bit bigger. So, I mean, there are things. For example, you can do that. This thing can ship a binary; it ships a signature with it, or something like this. It's one example. We haven't looked into this specific example yet. It's just one example of what the challenges are in this system, right? We have an untrusted component that needs to be able to request something from a trusted component. How do you build that sort of interface? I don't think we have a really good answer yet, but that's the sort of thing we're thinking about. Like, for example, cryptographic signatures. But for that, even you need to know what exactly is it, like how far, like if we don't trust this thing at all, then yes, you're right, we have to like completely close this communication channel. But if we trust it somewhat, then there is things we can do, and we're trying to figure out what those things are.
Okay, one more question here.
Thanks. So you've motivated the need to secure this BMC against some vulnerabilities, but can you quantify or demonstrate that this BMC is securer than the one you originally had? Have you tried pen testing or?
So the short answer is no. The longer answer is we are. So in our hearts, we're systems people. We're not hardcore security people. We are currently more worried about that thing by itself screwing it up. We're more worried about, I mean, we write that code. I don't necessarily trust the code I write if what I'm dealing with is this big network. I want some tool that tells me, yes, you did it right, and if you turn this on, you're not gonna smell burnt silicon. And then, I mean, the same goes. If we now start having other components on the system, we don't want them to mess with it. That's where we're coming from. What exactly our demonstration would be for comparing this sort of system against another one? I mean, I guess pen testing is one. We have security people at ETH as well that we would, of course, that we are in contact with and that we would be talking. And I think David actually has more to say about it.
Well, I was just going to say that at the moment, this project is largely driven through Daniel's PhD thesis. If I had funding for another PhD students to look at the penetration testing and like from a security aspect, then we would love to do it. Is the short answer, right? Is that it's a manpower. Yes, absolutely we should.
Cool. Was there one more comment, last question before we move to the last talk? There was.
So maybe one of the comments. So even though the web server has a red X, that doesn't necessarily mean that, for example, we cannot use cryptographic protocols such as WebAuthn or something, or hardware tokens, for example. Like you can only call into the power manager if you supply a signature generated by a hardware token issued to you, and then that would allow you to use what is essentially an untrusted interface and maybe separate the authorization of people operating that interface, like. So that was common to the web server thing.
So okay, one last comment from me. Because cyber retrofit turned up in this talk, there is a nice cyber retrofit technique as well for protecting communication between untrusted and trusting component, which would be filtering. So if you're worried about attacks that just randomly spew stuff at the power manager, you could put a filter component in between as well that does that. More in the Hackens paper for that. And with that, thank you for your talk.